18 a little differently than the way it's presented in the book. When we have equilibrium, we want to figure out, where does it end up? Like, for example, water. Water was mostly water molecules and a tiny bit of hydronium and hydroxide because it was so uphill in energy. Very few water molecules can roll that far uphill. Well, what tells us the balance, once the reaction's done, is something called K. This is capital K. And this is called the equilibrium constant. The equilibrium constant tells us the ratio of products over reactants. So K, remember what was it called? KW? That's the equilibrium constant for water. Was that big number or was it a really small number? It was a small number. It's 10 to the minus 14. 10 to the minus 14 tells us it's like 1 part to 10 to the 14 parts here. And so what that tells us is that it's mostly reactants, very little products. Whereas a big ratio, like 10 to the positive 14, tells us it's all product, no reactant. Whereas a ratio that's close to 1 tells us it's more of a 50-50 mix of product and reactant. And so K is going to tell us the balance at the end. So KW is the most important K you're going to deal with in this. There are other Ks in this chapter, but we're going to skip them. And so we're just looking at this, the ratio of products over reactants based on this equation is K. Now once we hit equilibrium, that ratio's got to be maintained. That ratio is a constant. And so we can screw things up here. Actually, let's take a look at this one really quick. No matter how we do the reaction, these are just different starting conditions. The ending conditions have to meet that ratio. So here's that ratio. The ratio is 51.5, 51.5, 51.5. So they did this reaction 4 different ways, and they always end up at that ratio. That's the significance of the equilibrium constant. Now, once you hit this equilibrium, then it's possible to screw it up by adding more reactant or removing product or removing reactant. We could screw things up. And so let's take a look at this. Let's say equilibrium has been hit. It's methane, hydrogen sulfide, hydrogen carbon disulfide. So we have an equilibrium here. There's some sort of balance. What would happen if we add more H2S? If we add more H2S, then we're going to have too much reactant, not enough product. So what happens is called a shift. That is, we're going to shift it right. We're going to have to make some more product to balance it again. This is called Le Chatelier's shift. This is called Le Chatelier's principle. And so if I add more H2S, then it's imbalanced. And it's got to shift to achieve that balance. So it shifts right in this case. What if I increase the H2? H2 is a product, so now I have too much product. It's got to shift to the left. Yeah, the shift to the left. And so those are Le Chatelier's shift. You just predict the direction of the shift. And so increase H2, it shifts forward. Increase H2, it shifts reverse. Pressures can impact things as well. Pressure is going to favor the side with fewer moles of gas. And so let's take a look at this. If we look at this, this is gas, gas. This is 1 mole, 2 moles, altogether 3 moles of gas. This is solid, this is gas. Altogether 4 moles of gas. Solids don't take up that much volume compared to gases. Gases take huge volumes. And so which side favors smaller volumes? Which side favors bigger volumes? The side with less gas favors smaller volumes. The side with more gas favors larger volumes. So if you were to compress this, what happens is it's got to shift to the left because the left side takes up less space. And so let's take a look at predict the direction of the shift. If the volume is reduced. If the volume is reduced, then the shift is to the left, reverse. That's what we do here. The temperature also has effect. The temperature is going to favor the endothermic. Increasing temperature favors endothermic direction. So if we add more energy to this, it's going to shift it to the right. If we remove energy from this, it shifts it to the left. So this is view here, Le Chatelier. And so here we're decreasing the temperature, it's going to go left, reverse. Okay. And so that's Le Chatelier's principle. So once we hit this equilibrium, so there's a couple of things. K, the equilibrium constant, tells us the ratio. KW is a very important ratio to know. And then Le Chatelier's principle. Le Chatelier's principle tells us the shift. Now, the last part of chapter 18 deals with calculations using K. The calculations using K, we're going to skip those, except for one, the ones that we did for KW. But the same type of calculations can be done for other reactions as well. And so there's something called KSP here for silver chloride. ASP stands for solubility product. There's something called Ka for acid solutions. There's something called Kb for base solutions. Kw for water.
We just need to know KW.
You just need to know Kw. We aren't going to do Ka, Kb, KSP. Common ion effect and buffers. This is all Chem 1B. But we don't have enough time to do it properly. Let me skip it. And so let's just do one KW calculation. If we look at KW, KW describes this reaction. H2O liquid plus H2O liquid. This goes to hydronium plus hydroxide. Now, it turns out that the KW is going to equal the concentration of the hydronium times the concentration of hydroxide divided by the concentration of water times the concentration of water. The concentration of water, these don't change, don't really change. Let's say if you have 1 gallon of milk versus 2 gallons of milk, is 2 gallons of milk twice as concentrated? No, it's the same concentration. The same thing for water. If you have 1 gallon of water versus 2 gallons of water, is 2 gallons of water more concentrated? No. And so these are left out. Pure liquids are left out, and so we end up with Kw is equal to the hydronium ion concentration times the hydroxide ion concentration. We set up an ice table like this. An ice table is ICE. And then we fill in the blanks here. This is a typical calculation. And so initially, what we'll have is, let's say, 1.0 times 10 to the minus 7 molar, 1.0 times 10 to the minus 7 molar. And we call that pure water. But what happens if we add acid to this water? If we add acid to this water, let's say I'm going to add 0.1 molar acid. And so what I'm going to do is I'm going to perturb this equilibrium. This is Le Chatelier's principle in action. So perturb this equilibrium by adding plus 0.1 molar HCl. 0.1 molar HCl is 0.1 molar hydronium, basically, because it's going to split up that way. And so this is going to be here, plus 0.1 molar hydronium. And HCl doesn't have any hydroxide, so this is just going to be plus 0 molar hydroxide. And so, at the end of this, I'm going to get 0.1, and then 0, 0, 0, 1, 2, 3, 4, 5, 6, and 0.00000. I need 6 zeros. 1, 2, 3, 4, 5, 6, and then a 1, 0 molar. All right, so I'm going to have something like this, but this is no longer going to be at equilibrium. I've upset the equilibrium. And so what's going to happen is the equilibrium is going to be reestablished. So there's going to be a change to reestablish. This is Le Chatelier's principle. So if I add more hydronium, which way is it going to shift? If I add more product, the equilibrium should shift to the left. And so what this is going to do, how much it shifts, we don't know yet. So we'll just call it minus X molar, minus X molar. And then we do et cetera. And so this would be an example of the type of calculation you would do with K. Since the calculations are kind of involved, we're skipping the calculations to make it a little easier for us. Okay, so that's it for chapter 18. For chapter 19, chapter 19 deals with redox reactions. So we already talked about redox reactions.
Wait, so if we're going over chapter 18 on the slideshows and taking notes from that to kind of supplement this, which part do we skip in chapter 18?
Which part do we skip from chapter 18?
Yeah.
Everything until constant, equilibrium constant.
Yeah, we skip all the calculations except for KW. All the K.
The only thing we know.
These types of calculations we skip.
So,
We just did up to Le Chatelier's, basically.
And then after that, we don't need to know.
Well, you need to know K. The most important K is
Right.
KW.
KW. You need to know KW.
But other than that and KW, because all the other calculations we don't need to know.
Right. The other calculators are gonna look like this, so you don't have to do that. All right. Here, I'll go back. Let's look this out then. Back to this. So I said I was going to go a little bit out of order. A little bit out of order is I talked about this first, the equilibrium constant. So what does that represent? It represents the balance, right? And then we backtrack to Le Chatelier's. Le Chatelier's is if you upset that balance. Once that balance has been established, you can perturb it. So Le Chatelier's, if an equilibrium system is subjected to change, processes tend to partially counteract the initial change. If an equilibrium system is subjected to change, brings the system to a new position of equilibrium. That's a very wordy way of saying it's just going to shift one way. So then I just jump to this slide. Okay. But what that means is I skipped. How many slides did I skip? Here's where I ended. This is slide number 37. So I'm skipping slides 38 through 60. So you can do the same. Skip slides 38 through 60. I'd like to cover that in more detail. You'll probably forget it anyway by the time Chem 1B comes around, just one semester later. You don't do those kind of calculations in Chem 1A at all. And so I decided not to bother. Yeah. Well, redox reactions, one of the biggest applications of redox reactions are batteries. Redox reactions are electron transfer reactions. And so how do batteries work? And so let's just take a look at this battery here. How the battery works is you have to separate the oxidizer from the reducer. So what they did here is they put the oxidizer in this beaker. The oxidizer here is copper 2. Over in this beaker they put the reducer. The reducer is zinc metal. And so the copper too wants electrons. And so it's going to try to take electrons from anything it's in contact with. Will copper too take electrons from water?
No.
No, it's too hard. Will it take it from glass?
No.
It will try to take it from copper metal, but will it be successful? If copper 2 oxidizes copper metal, we're just going to form copper 2 and copper metal, the same exact stuff. But we have to recognize that metals are a sea of electrons. So copper 2 is going to pull on these electrons, but it's not going to be successful in pulling it from copper. But if the copper is attached electrically to zinc, and so what we have is a chain of electrons. And so the copper pulls on electrons here, and it's felt. It's felt all the way up, all the way through here. It can't, this is copper wire probably. It can't pull them off the copper wire. This is tungsten light bulb. It can't pull it off the tungsten, but it's pulling, and it's being felt. It's going to be felt all the way to zinc. Can copper 2 take electrons from zinc? Yes. And so what's going to happen is this. The oxidizer's over here, the reducer's over here, but the electrons, it's going to take the electrons from zinc, and the electrons are going to travel through this, what we call an external circuit, light up the light bulb, and then copper 2 can have them. And so this is how a battery works. We separate the oxidizer from the reducer. Here. Well, there's some jargon that's associated with this. The copper 2 takes the electrons. When copper 2 takes 2 electrons, it forms copper metal. This process is called reduction. The oxidizer gets reduced. That's what he's saying. What reduced the oxidizer? The reducing agent. The reducing agent is zinc. The zinc was oxidized in the process. Who oxidized zinc? Copper 2 oxidized zinc. And so zinc oxidation, copper 2 reduction. Now, the way people remember this is oil rig. Oil is oxidation is loss of electrons, so zinc loses electrons. And rig, reduction is gain of electrons. Copper 2 gains electrons. So oil rig. Now, what's going to happen here is the copper 2s are going to disappear. And this is probably copper 2 nitrate. Nitrates are still there. So if the copper 2s are disappearing, we're forming copper metal, the nitrates are going to be very unhappy. The nitrates are going to be very unhappy because there's no cations, it's all anions. And so what has to happen here is we need cations to, basically we need cations to compensate for the loss of copper 2. Where are we going to get cations? Well, we have to get some volunteer cations. Those volunteer cations can come from this, the salt bridge. The salt bridge is just some salt, in this case potassium sulfate. And so rather than having copper 2 here, we'll replace it with 2 potassiums. So 2 potassiums for every copper 2. So the copper 2s get consumed here, form copper metal, and the 2 potassiums will come here and take its place. That way it keeps the nitrates happy. Otherwise we're going to generate huge static electricity, which is going to stop the battery from operating. Since the cations go this way, we call this the cathode. And this is called the electrode. The electrode is, where the electrons, the conduit for the electrons. Usually a piece of metal or some conductor. And so this is the cathode electrode. Over here, we're going to be forming zinc. Well, zinc 2+ is unhappy by itself. It needs anions. Even though it doesn't precipitate, it'll be happy with sulfate. Having sulfate there is better than having nothing. And so for every Zn2+ that's produced, 1 sulfate is going to come over from the salt bridge and will be electrically neutral. No precipitate though, there's no precipitate here either, but electrical neutrality will be the key. And so this beaker here is called the anode. The anode is because anions have to go here to regenerate cations. Anode is where we generate electricity or electrons. Cathode is where we consume them. So the cathode is going to be positively charged because there's going to be a pull for the electrons. The pull is coming from the copper 2. The anode's going to be negatively charged because that's where the electrons are going to be generated, and the electrons are going to travel over to the cathode. And so the cathodes travel A to C, anode to cathode, alphabetical. So these are the parts. The net reaction is shown here, the copper tube and the zinc. What we're doing though is we're not allowing the copper tube to take the electrons directly from the zinc. We're allowing the copper tube to take the electrons indirectly from zinc, and this is how you can generate electricity. This is called an electrochemical cell or battery. We have the salt bridge, we have the electrodes. You know, the two electrodes we have, the zinc was the anode, copper was the cathode, connected by a wire. This wire, if you put a light bulb there, you can generate light. Skip this. We talked about oxidation, oil rig. Oxidation is loss, reduction is gain. We didn't talk about half reactions. The half reactions are these. Do you know why they call these half reactions? These are called half reactions. These are called half reactions because they're only half the reaction. They're half the reaction because we can't bottle electrons. If we could bottle electrons, then it'd be a full reaction. We can keep those electrons as a product. The same thing here. Can you sprinkle electrons into the water? No, you can't. And so this is a half reaction. The electrons have to come from somewhere else. Where do they come from? That's why they're half reactions. They're going to come from the other half of the reaction, from the electrons. If we add up the two half reactions, we get the net redox reaction, and this is an electron transfer reaction. So this is a wordy slide showing that. Okay, this is another redox reaction. We could make a battery out of this one as well, except this is not a battery here. Because here, do you see the blue solution? It's copper 2. And then this piece of metal here, the silver one, is zinc. And you can already see there's lots of reaction because do you see the copper crystals on the zinc?
Yes.
The electrons are being transferred directly. If the electrons are being transferred directly here, then we can't use it to generate electricity. And so eventually, yeah, all the electrons are going to be transferred and the battery would go dead, except this is not a very good battery because we need to keep them separate. You got to put the oxidizer on one side and the reducer on the other side. Otherwise, we can't power any devices. The same thing here. This is another redox reaction. This is direct, though. The electrons are being transferred directly. You know, we got silver ions. Silver ions can easily oxidize copper. So silver ions come, oxidize the copper. It's going to plate silver crystals on here, and then the copper is going to be oxidized and go in the solution here. It's going to be copper 2. They show it as a +1, but it's actually a +2. It's after several days. We saw that reaction before. All right, so here we're just going to do some half reactions. We're going to look at the two half reactions here. Iron 2 is the reducing agent or the oxidizing agent? Reducing agent. Iron 2 is the reducing agent. Is iron 2 oxidized or is iron 2 reduced in this half reaction?
Oxidized.
It's oxidized. So iron 2 is the reducing agent, which gets oxidized. Aluminum 3+ is the oxidizing agent, which gets reduced. How do we combine them? Well, we have to combine them such that the electrons cancel. If you look, how many electrons does iron 2 produce? 1. But if you look at if you look at aluminum, it needs 3. It's mismatched. Well, it's really easy to match those up. We just multiply by 3. And so you can see I need 3 for aluminum, and I'm only generating 1. Therefore, I have to triple the amount of iron here. So if I triple this, then I get 3 electrons. So that's perfect because that's exactly what I need for aluminum. And so if I look at the reduction half, it requires 3. The oxidation half produces 3. Now I can add these up. When I add these up, the electrons have to cancel. The electrons generated have the equal electrons consumed. If they don't cancel, that's a problem. It's a problem because free electrons are very unstable. Aren't going to exist. So now we add this up. This is the net reaction. There are 3 moles of electrons transferred. And so we could do this stoichiometrically. If we want to figure out, how much electricity is generated, for every mole of aluminum, we get 3 moles of electrons. For every 3 moles of iron, we get 3 moles of electrons. Figure that out. So this is the redox reaction. Is there a driving force for this? We'd have to see, what's the stronger oxidizer. Aluminum 3 plus versus iron 3 plus. Which one's stronger? Or which one's a more active metal? Aluminum versus iron 2 in this case. So we had to multiply by 3. So let's take a look at this cell in more detail here. Okay, we like to draw it like this. We like to draw it so the electrons go left to right. That means over here on the right, we draw the cathode. So it goes A, C, anode, cathode. And we look at the cathode first because the cathode is going to pull the electrons through the wire. And so what's pulling the electrons through the wire? It's the oxidizer. In this case, the strongest oxidizer present is copper 2 plus. And the copper 2 plus wants 2 electrons to plate copper metal. So that's what's happening here. Okay, where is it going to come from? Well, over here, it's going to come from zinc. Zinc is easy to oxidize. It gives up the electrons without too much difficulty. And so this is the exact same cell that we saw earlier. The only difference is rather than a light bulb, they put a voltmeter on here. Now, a voltmeter is going to measure the pressure on the electrons being pushed through the circuit. And so if there are high volts, then these electrons are really being pulled hard through the wire. Low voltage means they aren't being pulled that hard through the wire. And there's going to be some resistance here because zinc doesn't give up its electrons without a little bit of a fight. And so there's a little bit of resistance here with zinc, but copper 2 is going to win. And it's going to win with a net pull of 1.1 volts. 1.1 volts. Well, we can calculate, what if we use, rather than zinc, what if we use iron here? What if we use iron? Would iron hold on to its electrons more tightly than zinc? Or less tightly? And so what we can do is we can figure that out by I'm going to have to, by going to another chart here, like this. And so that's where these numbers come in here. Right here. All we do is we add up the 2 numbers. So, for example, that last cell was copper 2 plus 2 electrons. Copper 2 plus 2 electrons yields copper metal. If we go over here, that's plus 0.34 volts. And then zinc, well, it's the reverse of this one. So what we have to do is we have to flip this one around. If we flip this one around, then we change this sign. And so rather than being negative, it becomes positive. And so zinc goes to Zn2 plus 2 electrons is positive 0.76 volts. So plus 0.34 plus 0.76 gives us 1.1 volts. So that's why that cell is generating 1.1 volts. If we use iron instead, well, this is iron here. We flip it like this. It turns out iron's harder to oxidize. Iron's harder to oxidize. It's only going to be plus 0.44 volts. So if we use iron instead, we have 0.34 plus 0.44, which gives us 0.78 volts. And so if I did the exact same thing but used a piece of iron, I'd get 0.78 volts rather than 1.1 volts. So that's where these numbers come from. But that's just to tell you, because we aren't actually going to do the calculation, it looks like, in chapter 19 there. All right, so that's your introduction to batteries. This is a different kind of cell. Here. A battery is called a voltaic cell. The other kind of cell is called an electrolytic cell. In an electrolytic cell, what we're doing is we're using a battery, or we're using electrical power source to force electrons in the reverse direction. So let's say you have a secondary battery. Secondary batteries are rechargeable batteries. In a rechargeable battery, what you can do is you can put a power source here or a bigger battery and force the electrons backwards. So normally the electrons go left to right. If we put a power source here, we can force force the electrons to go right to left. If we do that, then not only can we recharge batteries, but we can generate unstable chemicals. And so electrolysis is used to generate things like chlorine gas, which is unstable, or even sodium metal. In fact, that's how they generate sodium metal and chlorine gas. A lot of it's just by electrolyzing salt. Not in water, but molten salt. So this is NaCl. If you look at it, it's liquid. So if they force the electrons to go backwards, the sodium ions pick up an electron to form sodium metal, which floats to the surface. Chlorine ions lose an electron to form chlorine gas. So we form sodium metal and chlorine gas. We have to have a barrier here to protect the sodium metal from the chlorine, otherwise sodium and chlorine react violently with one another. All right, that's a little bit about batteries. We'll come back to electrolytic cells and electrolysis, and then we'll look at redox reactions again. But I'm going to stop here a little early. I have to leave for a meeting. So.